All right, so in today's lesson, we're going to be looking at lesson 3, concavity, all right, which we talked about a little bit in lesson 2 when we looked at points of inflection, and we noticed that, at some point on some of the graphs we looked at, the concavity changed from a downward concavity to an upward concavity. All right, so at the top of the notes here, I have some vocabulary review just to remind you. We have a turning point, points where the direction of the function changes. Maximum is a highest point, minimum is a lowest point. We talked a little bit about relative or local versus absolute versus global. When we're talking about a very specific region on the graph, we're referring to a relative or local area as opposed to the whole graph, which would be absolute or global. Increasing, that's where the values are getting larger as x gets higher. Decreasing, the values are getting smaller as x gets higher. And the end behavior is basically what it says, looking at the ends of the graph. And just as a reminder, I have an example here demonstrating some of those different concepts. All right, so let's get right into it. The first thing we're going to do is just note that how would we find the concave downward on an interval? You're going to be looking this time at the second derivative. This is sometimes called the second derivative test. When the second derivative, when the interval of the second derivative is less than 0, we know we have a concave downward part of our graph. A curve is concave upward on an interval when the second derivative is greater than 0. I should say greater than or equal to, and less than or equal to 0. So pretty easy. We're going to just take our function and find the second derivative to start. And we're going to use the power rule. Nothing too difficult here. 2 times 3 is 6. 3 minus 1 is 2. And that's our first derivative. And now we're going to take the derivative of the derivative to get our second derivative. All right, and then what we do is, just like when we were using the first derivative to find intervals of increasing and decreasing, we would set it equal to 0. That's what we're going to do here. So we're going to take our second derivative and set it equal to 0. And I'm going to pull out a GCF. I'm going to set 2x minus 1 equal to 0. I'll get x equals a half. Alternatively, you could have also, instead of what I did there, you could have said, 12x equals 6, x equals 6/12, which means x equals a half. Either way is fine. All right, so now we have our critical value identified for concavity. So we're going to draw a line here. We're going to do a sign diagram. We're going to plot our critical value that we got when we took our second derivative and set it equal to 0. And just like when we tested for intervals of increasing and decreasing, we put in test values, only this time the test values are going to go into the second derivative. All right, so I need a value before 1/2, and I'm going to pick a nice easy one, which would be 0. And I'm going to need a value after a half. And of course, I'm going to pick another easy number, which would be 1. If I put 0 into my second derivative, right, 12 times 0 is 0, I get negative 6. And if I were to put 1 into my second derivative, 12 times 1 minus 6, I'm going to get 6. So again, we're just going to be concerned with the sign of the value that we get when we use the test. So I get a negative 6. So I'm going to put a negative here. I get a positive 6. I'm going to put a positive here. And this means that we're going to be concave down. All right. before 1/2, and we're going to be concave up after 1/2. So how would we write that? We would say concave up, that's where x is greater than or equal to 1/2. And remember, we're just talking about intervals. We're not really talking specifically about x values. So we're going to include the equal sign in both concave up and concave down intervals. And it's concave down where x is less than or equal to 1/2. All right, let's take a look at another one. Now we're going to kind of put it all together here. It says, for the following function, determine the intervals on which we're increasing, decreasing, concave up, and concave down. So we're going to take the first derivative. We're going to set our first derivative equal to 0. We're going to have to factor with a leading coefficient other than 1, so I'm going to do my kung fu trick here, make a rainbow. Then we're going to rewrite the x squared without the leading coefficient. The middle term doesn't change. Put the -6 on the end. Now we're going to factor that easier trinomial. So we're going to use, let's see, +6 and x minus 1, and that'll work, right? Now I'm going to apply the trick, which means I'm going to take that leading coefficient and I'm going to divide it by each of the second terms of those two binomials. Next step, I'm going to simplify. Don't forget to simplify. And if you can't simplify, you just bring that 3 in front. All right, so we get x plus 2 times 3x minus 1 equals 0. Now you certainly can factor it however you want. That's just a way that I've been demonstrating in class that seems to work well for a lot of people. Just a reminder about that. Factor it however you want as long as you get here. Now we're going to solve for x because we have x plus 2 equals 0. So we get x equals -2 and we get x equals 1/3. So we have two critical values for our number line for increasing and decreasing intervals. Well, let's see, -2 comes before 1/3. Decreasing where x is greater than or equal to -2 and less than or equal to 1/3. All right, now we're going to take the second derivative. So we take the derivative of the first derivative, and we're going to get 6x plus 5. We're going to set our second derivative equal to 0. So we're going to get x equals -5/6. So that's the critical value we'll use for our second derivative test where we're checking for concavity. Our critical value in this case is -5/6. So now we're going to use the second derivative. We need a value before -5/6, so I'm going to pick -1. That happens to be -1. We need a value after -5/6, so I'm going to pick 0. So that's going to give us 5. So we get negative and we get a positive. So we're concave down. And then we're concave up. So if we write out our intervals, we're going to say concave up. That's going to be happening where x is greater than or equal to -5/6. And we're going to say concave down, where x is less than or equal to -5/6. All right, that's that one. Now, what I would suggest as usual is I would hit pause on the video right now, and I would see if you could do as much of this, on your own, and then check your work. So same thing, we're going to check for increasing, decreasing, concave up and concave down intervals. And we're going to take the derivative of this function. Now, the way to take the derivative is noted in your formula booklet, right? If you recall, if your function is ln of x, then f prime of x is equal to 1 over x. If your function has a derivative of so if in other words, if we have ln of u, and u has a derivative, the derivative would be 1 over u, but 1 over u times u prime. All right, so here we don't have a derivative for that part of our ln, and here we do have a derivative and we have to include it, and that is the case that we have for this problem. So with f prime of x, we're going to write 1 over 2x minus 1 times the derivative of 2x minus 1, which is 2. So this derivative is equal to 2 over 2x minus 1. Now, if you remember, and we haven't looked at a lot of these, we said that it is important to note when we're looking at increasing and decreasing intervals where the first derivative is equal to 0 or where the first derivative is undefined. So we need to determine, all right, because we have a denominator here, we need to determine where f prime of x is undefined. So in other words, we're going to take 2x minus 1 and set it equal to 0 and see what value would make this equal to 0. 1/2. If I put 1/2 into my denominator, I would get 0 in my denominator, and that would make the function undefined. So the critical value that I have in this case then is just 1/2. All right, we're going to use test values before and after 1/2. Let's see here. So I got decreasing and increasing. So we are increasing where x is greater than or equal to 1/2, and we are decreasing when x is less than or equal to 1/2. All right, now we're going to take the second derivative of the first derivative. We're going to take the derivative of the derivative. And we have to use our friend, the quotient rule. Let me write the quotient rule off to the side here. G f prime minus f g prime all over g squared. All right. So we have, and let me just make a note for you. This is f and this is g. So g f prime, now the derivative of a constant, the derivative of 2 is just 0, minus f, and the derivative of the denominator, the derivative of g is 2, all over g squared. So when we clean that up, we end up with -4 over 2x minus 1 squared. And again, we have a place where we have to determine where it's equal to 0 or where it is undefined. To find a critical value, either of those would be the ways we would determine that critical value. So we are going to look at right here. So 2x minus 1 equal to 0. We're still going to get 1/2, just like we did when we did the first derivative. Our critical value then is 1/2. And we're going to examine the second derivative at a value before 1/2. And I think I will use what I used before. Just use 0. We put 0 into that second derivative, we're going to get -4. And if we put 1 into our second derivative, we're going to get -4. Oh, all right, so we get negative, negative. So what we would say here, since they're both concave down, we would just make a note that f of x is concave down. Okay, and there is no concave up. That is our function. All right, there was a lot in this lesson. If you need to, rewind, pause, do what you have to do. Good luck, and I'll see you next time.